to section 4.3 for your listening and enjoyment. So we're going to talk a little bit more about looking at the derivatives and trying to connect the derivatives, both the first and the second derivative, to the graph of the original function. So let's start with something called the first derivative test for local extrema. And we'll start with this graphic. And what do we notice about the local max and min in this graph? Well, here's one. Here's another one. Here's a local max that's also an absolute max. Here's one. No, that's not one at all, is it? Silly me. Okay, there's a local min here, and here's an absolute min, which also is a local min. So what do we notice about them? Yeah.
They are either the values at the end, at the two ends of the domain A and B.
Mm-hmm.
They're either when the derivative is equal to 0 or undefined. Those are at least the candidates.
Okay. So let's break this world into two groups: the endpoints and the interior. And on the interior, these local maxes and mins tend to happen where the derivative is either 0 or undefined. And then we got this thing. There's a derivative that's equal to 0, but it's neither a max nor a min. So what do we make of this weird one, which I'll do in blue, because it's really weird? All right, so there's a situation where we have a derivative that's equal to 0, but it's neither a local max or min. How is the blue one different than the red ones? What makes it different? But, yes?
Like, not all the points, it's not the highest, not all the points around, it's not higher than all the points around it, it's not lower than all the points around it, because it's increasing as it approaches in the,
Well,
I don't know how to do this one.
Over here it's increased, the function's increasing,
Right.
and then we get to
And
here,
it continues
and
to
then it
increase
continues to increase.
instead of changing direction.
Instead of changing direction. So let's say then one of the things we could look at in terms of finding these local maxes and mins is that not only do we have a either 0 derivative or an undefined derivative, but we also change from increasing to decreasing. Or we change from decreasing in this span to increasing. I saw a hand. I didn't see a hand. Yes?
I was going to say what I was saying.
Okay. So what I would like, because I'm a mathematician, I'd like to change this into a rule. I'd like to have something hard and fast that I can use so I can say, I know where to find the local mins and maxes. I would like a rule. And here is the rule. If we're in the interior, then let's only look at the critical points. The places where, again, we said the derivative is either 0 or undefined. If at a critical point, f prime changes its sign from positive to negative, which is another fancy way of saying it changes, the function changes from increasing to decreasing. If f prime changes from positive to negative, then f has a local maximum at C. If f prime changes from negative to positive, which again is another fancy way of saying that the function goes from decreasing to increasing, then we can say that there's a local minimum at C. Lastly, if there's a critical value and there's no sign change, it started negative, stays negative, or started positive and stays positive, then we say then the function does not have a local extreme. It's neither absolute or local max or local min there. And there's how we'll summarize. That's how we'll summarize the interior points. So far, so good? Now all we have to do is handle the endpoints. Shall we go back to our picture? Not yet. Okay. Yes, Ryan.
It says it applies to a continuous function. Does it have to be on an open or closed interval? Or?
No, these will work on places where the interval's open. It'll work on something that has got no restrictions on the domain, from negative infinity to positive infinity.
So
But the function does have to be continuous. That is true. All right, let's go back now to our picture. So over here, let's focus over here, where we have an absolute minimum, which happens also to be a local minimum. What can we do to look at, let's say, the derivative to determine whether that is a local min or local max? How about if I'm on the left endpoint of an interval?
What's happening to the right?
And what's happening, and what kind of derivative do we have to the right? Positive. So let's combine those things. If I'm on the left-hand side, and the derivative just to the right of me is positive, we have a minimum. If I'm on the left-hand side and the derivative to the left of me is negative, I must be at a local maximum. What if I'm on the other end?
The left is positive.
If I'm on the right end, and the derivative just to the right of me is to the left, sorry. Okay. If I'm on this end and the derivative just to the left of me is negative, I must be at a minimum. If I'm on the right end and the derivative just to the left of me is positive, I must be at a local max. And let's see if we can summarize it in words, because that might be a little bit easier. Okay. If we're at a left endpoint A, and f prime is less than 0, okay, this notation is awkward. This expression goes with this conclusion, and this expression goes with that conclusion. Ugh. I don't like the way this is written at all. Is it easier just to say, you look at what's going on right afterwards? If it's increasing, you're at a minimum. If it's decreasing,
Yeah, because it's.
you're at a maximum.
Yeah.
And if you go to the other end, if just before we get to the end point, you're increasing, you must be at a maximum. If you're at the other end, just before, if you're decreasing, it must be a minimum. Would that be better worded than what's there? No, this is a local, not absolute.
Oh,
That's,
I was like.
it's a math term. All right. So should we just bypass this one because this is more confusing than what's really going on?
Oh, I already started writing.
You already started writing.
It sort of makes sense. You just take out the parentheses.
Well, I just think they should have wrote it in 4 cases instead of 2 cases.
Oh, I see.
mathematicians are most definitely lazy.
We say that about scientists too.
What's that?
We should say that about everyone.
Is there anyone who's not lazy?
English people, because they have to write on it.
Yep.
In books.
Yep.
They don't use apostrophes. They don't make shortcuts.
Silly people. And they have all those extra U's, like in neighbor and color.
Different
He's talking about English people like English professors. He's
Oh,
talking about English people like.
I got it.
alright. So let's apply this.
One day I'm going to go on your website and look at the lectures just to recall random non-math related discussions.
I heard you argue with him on one of them the other day.
What were we arguing about?
I forget. You disagreed with something, but then you were wrong.
Okay. If we're going to use the first derivative test to test extrema for this function, our methodology is going to be first looking at the derivative of that function. In this case, 3x squared minus 27. I think I can clean that up to 3 times x squared minus 9, or 3 times x minus 3, x plus 3. Check my algebra, please.
Yep.
We're good? Now what I tend to do is after writing that out, I say, let's look at a chart which helps summarize what's going on. I say that there are zeros for the derivative at -3 and 3. When x is really large and positive, the value coming out of here is positive. When x is inside this interval, like the value 3, it looks like I get a negative value for the derivative. And when x is very, very small, which is the official way of saying large and negative, the derivative is positive. Let me do a quick calculation here. F of 3 is what? 3 cubed minus 27 times 3 plus 3, or that's 27 minus 3 times 27, 81, plus 3. What do we got there? Nothing I can do in my head very easily. What's that?
Negative 51,
I'll take your word for it,
I think.
right?
No?
Oh,
Negative
that's
1 plus
total,
30.
yeah.
27 plus 54 is 81. So this is negative 54. Negative 54 plus another 3 is negative 51. We're good there, right? So let me summarize in the AP language in which I'd like you to learn. Yes? Are you ready for the AP language? That which you are going to memorize so that you can transcribe it on the test and get full credit.
Sure.
Because f prime changes from negative, that's supposed to be an n, negative to positive at x equals 3, comma, 3, comma, negative 51 is a local minimum. Now, this is the answer to the question, where is a local minimum? Explain. Or where is the local minimum? Justify. That extra word, explain or justify, means that you have to give all those extra words.
Makes me die inside that kind of scale.
You think they're unsympathetic dying?
women, I know how you feel. Words are not my friend either.
Words.
Words are everybody's friend.
Okay, let me find the value of this function at negative 3.
57.
Oh, man.
Positive 57? I'll take your word for it. Are you ready for the ending line here? Because f prime changes sign. Changes from, in this case, positive to negative at x equals negative 3. Negative 3 comma 57 is a local max. Again, if they just ask you, where are the local maxes, you could just say negative 357. If they say again, explain, justify. Now, if I told you that, let's do this in black. This blank and this blank, you can change those to blanks, and that red statement there should be the subject of one of your cards. That's what I mean. I want you to memorize those words. If I underline this word or that part, and said, okay, everything else, that should be on a word, or that should be on a card, because literally, word for word, that's cash, that's points. That's going to give you the advantage over the other students. All right? All right. So there's first derivative test in action. How about we go on to another slide? Woo! Concavity. I'll give you examples. This is concave down. This is concave up.
Convex down.
Nope. This is concave up. This area is concave down. And right about here is where it switches. And that place where it switches from being concave up to concave down or vice versa is called an inflection point. So, do you think you could recognize concave down when you saw it?
Yeah.
Do you think you could recognize concave up if you saw it? Great. Now we've got to put nasty mathematics into this. Are you ready? So from the intuitive side, you can look at a graph and you can see concave up and concave down. From the mathematician side, though, we are going to use longer definitions. We say that something is concave up on an open interval I if y prime is increasing on that interval. y prime is increasing, not y is increasing. That just means the slope is going, the function is going up. When y prime is increasing, it means it's getting more and more steep in a positive direction.
Wait, I don't get it. It's an absolute value, or because isn't technically when it's concave out, isn't it?
Okay, let me show you the difference between. Think of this function. That function is increasing. Its y prime is constant. Now let's think of something that looks concave up. What's going on? Y prime there is about 0, right? Y prime there is 0. But y prime here is bigger and bigger and bigger. Concave up is related to the rate of change in the slope. When the slope is getting bigger, if y prime is increasing, we get a graph that is concave up. Yes?
Would that be if, like, if you like reflected that, so it's kind of more like an arch? Would that be anything?
So it's bigger.
Okay, wait.
negatives
So
than
you want me to look at the other side of this parabola?
So it's just becoming smaller negatives before it becomes positive, so technically
It's
still increasing.
very large negative here. But what happens to the slopes? They go from large negatives to smaller negative to smaller negatives. The value of y prime is increasing. Maybe this is negative 50, a really big negative slope. But by the time we get here, we're down at negative 1. Y prime got bigger, didn't it?
Yep.
And then down here, y prime is 0, and then it's becoming positive. So concave up behavior means a positive change in y prime. Y prime is increasing. Let's take a look quickly at concave down. Here's a really big positive slope. Slope not so positive, going to 0. What's happening to the value of y prime as we go on that path? It went from big to smaller to 0. And now it's turning negative. Y prime is decreasing on this interval. This curve is concave down. Now, this is our baseline definition. This is our money definition. This is really where, when I want to look at concavity, I look at the second derivative. The first derivative is the slope. The second derivative is a measurement of how the slope is changing. So when I say y prime is increasing, you know what that is a euphemism for? Y double prime is greater than 0. Y double prime, the rate at which the slope is changing. I want to see, where is y prime decreasing? That happens when y double prime is less than 0. So, concave up, y prime increasing, which is another way of saying y double prime positive. Concave down, y prime decreasing, which is another way of saying y double prime is negative. Okay, all of those words are great, but I have a picture to summarize it all. If the second derivative is positive, so I make two positive signs, it's concave up. If the second derivative is negative, it's concave down. Is that an image that you can hold in your mind?
We just write it.
explain.
No, you could translate that into notation.
You're right, it's in the
No, you will actually translate that to f double prime of x is greater than 0. F double prime of x is less than 0. Now, besides this y prime is increasing, or this definition looking at the second derivative and when is it positive, when is it negative, there's one other way that the AP in this book throw the idea of concavity at you, and that is having to do with tangent lines. Every tangent line on a curve which is concave up, all those tangent lines reside below the curve. So they may say a curve is concave up, but they could say, give you the same information by this portion of the curve, all the tangent lines are below the curve. It's saying concave up in different language. When we go over to the stuff that's concave down, and I draw the tangent lines here, all those tangent lines reside above the curve. So if a curve is concave down, the tangent lines are above the curve.
Or did it just get punched in the mouth?
What's the other one?
Or he has Twizzlers on his face.
That's,
Is that what you're saying?
yeah, Twizzlers, that could be it.
What's the one into the other one?
I don't know, what name a green stringy candy? I don't know.
Gummy worms.
Sour patch straws, whatever.
Gummy worm.
The sour
It ate rigatoni.
Yeah, those straws.
Or a candy cane that's just green.
By the way, just because it sort of comes up, if it's not Twizzlers, if instead it is
Red vine?
not red vines, red laces, strawberry laces. I had to find strawberry laces for my wife. I had to go all the way to Clawson to get them. They have the hugest candy store I have ever seen in my life in Clawson.
It is my favorite.
Doc's candy.
What's that?
Stores.
You have nothing else, but we have candy.
Well, you also have good pasties in Clawson.
Okay, we have
Oh,
food.
yeah.
That's it.
And the dream
Wonder Drown.
birthday party location for girls 8 or outside the box. Girls less than 8 dream of having their birthday party at Step Outside the Box. What's
Is
that?
on Main?
It's on Main, just south of 14, right? Yeah. Okay. So enough digression. Trevor, you're gonna tag that and you're gonna put that in the collection of Fedor saying random things. Okay. All right.
I'm gonna give you my Facebook. Or not my Facebook, my laptop background when I get home.
Okay. Please discuss the concavity of the curve f of x is equal to x squared on the interval from 2 to 8. You could do it, by the way, 2 ways. You could just know what that curve looks like and you could tell me. But I would like you to actually use the definitions and stuff that we just talked about.
Okay.
Clearly, because it shows a smiley face.
So wait, Mr. Fedor.
Yes.
So you take the second derivative, right?
So first we take the first derivative.
So clearly, it's a
So
smiley face.
You take the derivative.
F prime of x is equal to.
You take the derivative of that, you get 2. And that's always positive, so it means it's concave up.
Because f prime of f double prime of x is equal to 2, which is greater than 0 on the interval to 8. F is concave up.
So that's an official math term.
Notice I never used the word it. did you, did you write f of x is concave up?
I said concave up, b/c, y, the second derivative of y is greater than 0.
Okay. Yeah, I mean, if I left this part out, that'd be okay. Yes?
What would you do if I marked it as because double prime of x looks like a smiley face? What would you do if I put that?
I would giggle and then mark it wrong.
What? No L?
Is there good addition because at
Hello.
the top of the test, you know, like teachers just put like a happy face at the top, you got a good grade, you should try that. What's that face?
Yes, this test makes me concave up. All right. Here's our definition for a point of inflection. A point in the graph where the function has a tangent line and where the concavity changes is a point of inflection. I don't know why, I think I'll probably find out later, why the function has to have a tangent line for it to be a point of inflection.
Well,
You can have functions that are defined but don't have tangent lines, i.e. that the derivative doesn't exist there.
so it must be differentiable.
You must have a first derivative. So I don't know. That it has a tangent line is different than the Stewart book that I was used to. It's okay.
Why did you change books?
Because the Stewart book was really a college book, and didn't have a lot of the kind of things that we thought would help the students do better on the AP exams particularly. And they were, the books we had were 11 years old, falling apart. All right, so there's a definition for point of inflection. May I go to the next slide, please? Yes?
Yes, you may.
All right, so would you please find all the points of inflection for the graph of y is equal, you can't read that. You need that bigger. Y is equal to 2e to the negative x squared. That's what it says.
I don't want to find it as much of that.
You don't,
I saw a dot, but that was just there.
Okay.
so what's the methodology here?
Find the second derivative
We need to do the second derivative at least.
and find where,
How about everyone work in your pairs and find the second derivative, please? I'll give you a hint. Find the first derivative first. I'm full of jokes today.
There's the derivative of the second, so derivative of e to the x is e to the x is 10.
Because you gotta do
Times
change
ln.
e to the x is e to the x, d to the x. It's just
So I
one
choose
over
like e to the so.
What is that, how the
two
same
in the
rule?
Well, I'll
I'm simplifying. Y
as a side note here, I'll write out that rule.
negative x squared times the change.
And the mantra is repeat, change.
Oh, yeah.
And it has to come up front.
Okay?
Plus second. There's zeros.
Really tight. Really tight. Friday I was kind of laying in bed and I realized I would lay my hand out and then curl up again. It's like I'm so tight I do that right?
That's it.
That's the first derivative.
Yeah, that's,
Second
Like
derivative,
that.
which is much higher.
oh, no, you had it right.
First
Minus 4.
times the derivative of the second
Minus 4e to negative.
plus
I didn't have it right.
the second times the derivative of the first. But that's not the answer I want.
2 or 4 times
I want to factor it.
4e, or e to the negative x squared times the quantity of minus 1. So x squared minus 1.
Okay, now let me tell you why I want to do that. When I get these e to the x's, it's really important, if you can, factor all of them out, because one of the things that we're going to try to do is we're going to try to say, when does that sign on the second derivative change? When does it go from concave up to concave down? It's where the second derivative changes from negative to positive or positive to negative, and that tends to happen where? Where the derivatives are zero, the second derivative is 0. Now, this expression here, 4e to the negative x squared, it's never 0. Never 0. It approaches 0, but it never gets there. So all the zeros are going to be on the other things, the things that are left over. When does 2x squared minus 1 equal 0?
Plus and minus.
1/4?
Or,
No.
Plus or minus
Oh, wow.
1 over root 2, or plus or minus root 2 over 2. And so when I get into a discussion of concavity at this point, I'm going to do that same sort of sign chart that we talked about. Here, oh, what do we call it? Oh, we call this y prime, right? This time. Let's do this in what color? Red. Y double prime. It's equal to 0 at negative root 2 over 2 and positive root 2 over 2. And now I ask, hey, what kind of signs do we have in those different intervals? Well, let's do the easy one. How about at 0? I take the 0, I go and put it into this expression that y double prime is equal to, and it looks like I get, put a 0 in here, I get a negative there, this thing's always positive,
Positive
negative there. What about when x is big and positive? Put a big and positive number here. Again, doesn't matter what's going to go on there. That value, that expression is always going to end up being positive.
so it'd be positive. And the other one would be positive 2.
Yep.
Such a bad one. I thought we usually went off the values for y prime for this number.
Points of inflection.
That's when we're trying to find local
Oh,
max and minima. And by the way, for example, if you take a look at this, if you take a look at y prime, what kind of picture do we get? What kind of values of x make that 0?
none. Oh, wait.
Well,
Yeah.
remember, e to the power of anything is always going to be positive. So this is always positive, this is always negative.
0.
At 0, we get a critical value for y single prime. And when x is negative, this is positive over here. When this is positive, I get negative. Let's see if we can complete this picture. The graph of this is going to reach a local maximum because f prime changed from positive to negative at 0. There is a local maximum at 0, comma 2. This function is decreasing as we go to the positive side. This function is increasing to come up to that point. And then here at negative root 2 over 2, there's an inflection point. It goes concave up, concave down, concave down, concave up. Now these concavities are pretty shallow, but you can kind of see that there's a change. In the concavity of the graph.
So if it would keep going, it would just go up.
From here on out, root 2 over 2, from here on out it's concave up all the way. Or in other words to say, the tangent lines lie below the curve. And that's how we do these problems. You cannot read that at all. How about that?
So you just say there's points of inflection at this point and this point. You don't have to say it's concave up until this point.
Well, they just wanted to know where the points of inflection are. If we wanted to be more particular, we would yeah. They would call those, what are the intervals of concavity? On what intervals is the function concave up? On what interval is the function concave down? Things like that. Maddie, you not wearing your watch?
I don't know what happened.
What are we going to do?
I don't know. I pressed the button.
Press all the same buttons.
And we were trying to.
Okay, yes.
So do we have to find the zeros of y prime in order to find all the points of inflection, or
We have to find the zeros of the y double prime
Right.
in order to find candidates for points of inflection. Because the points of inflection are places where the sign changes.
so if the number line is looking like that, then those are our points of inflection. But if it's like negative, then that's not a point of inflection.
That's correct.
Then we have to find y prime once we've found y double prime to make
No,
sure we have this.
typically we add the maximum, local maxes and mins, and the points of inflection in one big package to kind of see what these graphs look like.
So we would have the y prime.
Okay. We're running short on time. I want you to get write down the assignment, and then I'm going to do one more example problem, which we may run out of time as we're doing it. So let's get the assignment written down, and then we're going to go backward. By the way, this puts us on pace for a quiz on Wednesday. Now, is anyone not going to be here on Wednesday? Okay. Field trips?
Yeah.
Okay. So I think we're actually going to delay the test till Thursday so you guys can be here. It'll be easier to do that way. Anyone not going to be here Thursday? All right. So can we go back and do one more example with our remaining less than 2 minutes? Yes?
Sure.
Okay. The last thing that we have here, one more bit of detail, and that is we can actually look at the second derivative to determine the location of local maximum and minimums. Here's the idea. Let's say I've got a curve, and that curve has a critical point where the first derivative is equal to 0, horizontal tangent. This curve also happens to be concave down. The combination of critical point and concave down, critical point, sorry, first derivative equals 0, and concave down means that there has to be a local maximum there. Has to be. If you have that combination, you have to have a local maximum. If I've got a concave up and I've got a horizontal tangent, that combination has to mean a local minimum. Or, as you might guess, because f prime of 3 is equal to 0 and f double prime of 3 is greater than 0, that means local minimum. All right? So we're going to translate that into a justify or an explain on the AP exam as well. All right. Come in with questions tomorrow. No. We haven't covered anything new.